All right, let's get started. Today, we're going to go on a little journey, a journey to completely rebuild our understanding of the universe. Seriously. It's a story that kicks off when classical physics seemed just about perfect, but there was this one tiny little crack in the foundation. And that crack, well, it was about to shatter everything we thought we knew for sure about space and time. It all boils down to one simple but world-changing question.
What if the speed of light isn't just, really, really fast? What if it's a fundamental, unbreakable law of the cosmos? The same for everyone, everywhere, no matter how fast you're going. I mean, just think about that for a second. If you take that one idea seriously, it forces you to throw out all your everyday common sense and build an entirely new, pretty mind-bending reality.
So, how do we get from here to there? Well, first, we'll look at the crisis in 19th century physics that basically made this revolution unavoidable. Then, we'll meet the two simple but incredibly powerful rules that Albert Einstein came up with to fix it all. From there, we'll dive into the truly bizarre consequences of those rules. We're talking stretching time, shrinking space, all that good stuff. We'll even tackle the famous twin paradox. And finally, we'll see how it all clicks together into this new, unified concept, space-time. Okay, let's dive right in. So I want you to imagine is the late 1800s. Physicists are feeling pretty good about themselves. They really felt like they were on the verge of knowing, well, everything. The universe seemed to run like a perfect, predictable clock governed by two magnificent pillars of physics. The problem was, underneath it all, those two pillars were at war with each other. Okay, so on one side, you've got Isaac Newton's laws of mechanics, and these are totally intuitive, right? If you're on a train going 50 miles per hour and you throw a ball forward at 10 miles per hour, somebody standing on the ground sees that ball flying by at 60. Velocities just add up. Simple. In this world, space and time are the fixed, absolute stage where all the action happens. But on the other side, you've got James Clerk Maxwell's equations for electromagnetism. These things perfectly described light, but they had a bomb hidden inside them. They predicted that the speed of light, which we call c, was a universal constant. It wasn't relative to anything. So how can both of those possibly be true? They're in total contradiction. How can velocities just add up, except for the velocity of light, which doesn't?
Exactly. That was the big problem. And to solve it, scientists came up with this really clever, if kind of desperate idea, the luminiferous ether. The thinking went like this. Just like sound waves need air to travel through, light waves must travel through some invisible substance that fills all of space. And this ether, well, it would be the one special, absolute reference frame in the universe. Light travels at speed c in the ether, and for everyone else moving through it, you'd measure a different speed. It sounds a little strange, but it seems like a pretty logical way to patch up the problem and save the old physics. And it was a logical patch. It led to one of the most important failed experiments in the history of science. In 1887, two scientists, Albert Michelson and Edward Morley, built this incredibly precise device to detect the ether wind as the Earth moved through it. They expected to see this very clear shift in a pattern of light. So what did they find? Nothing. Zero. A big, fat, null result. So wait, the ether didn't exist? What on earth did that mean for physics? It meant physics was totally fundamentally broken. The logical fix was just wrong. And that contradiction between Newton and Maxwell was real, it was unavoidable, and it was a genuine crisis. So into this mess steps a 26-year-old patent clerk, a guy you might have heard of, named Albert Einstein. And he didn't try to fix the old system. He realized the contradiction wasn't a problem to be solved. It was a clue to a much deeper truth. He decided to just throw out the old rulebook entirely and start over with two new, incredibly simple ideas, or postulates. Now, what's so amazing here is just how bold this is. The first postulate, the principle of relativity, says there is no special preferred spot in the universe, no ether. The laws of physics work the exact same for everyone moving at a constant speed. And the second postulate just takes that shocking result from Michelson and Morley and says, yep, that's a law of nature. The speed of light is the same for everyone. So if I'm standing still holding a flashlight, you see its light move at speed c. If I'm flying past you in a rocket at 99% the speed of light and turn on that same flashlight, you still see its light move away from me at speed c. Not 1.99 times c, just c. Okay, hold on. If the speed of light is absolute, then something else we thought was absolute has to give. And you're telling me that something is the very idea of two things happening at the same time? That just feels impossible. How does that even work? Oh, absolutely. This is where it gets wonderfully weird. Imagine Frank is standing in the dead center of a moving train car. At the exact moment he passes Mary, who's on the platform, two flashbulbs go off at the very front and very back of his car. Now, since Frank is right in the middle, the light from both flashes reaches him at the exact same instant. For him, those events were simultaneous. But what does Mary see? From her point of view, the train is moving. She sees the light from the front flash reach Frank before the light from the rear flash because that rear light has to catch up to the moving Frank. So for her, the events were not simultaneous. So who's right? They both are. Simultaneity itself is relative. And once you accept that, once you let go of universal now, a whole bunch of other bizarre effects just tumble out. See, if we can't agree on what happens at the same time, then we also can't agree on how long things take, or even how long they are. Space and time, it turns out, become flexible, stretchy things.
And this leads us to the first huge effect, time dilation. All it means is that a clock moving relative to you will be measured by you to be ticking slower than a clock sitting right next to you. So, wait a minute. You're telling me their clock actually runs slower. That can't be a real physical thing. It has to be some kind of illusion, right? It totally feels like it should be, but no, it is absolutely real. And this isn't some trick of perception or a mechanical problem with the clock. It's a fundamental property of time itself. The rate that time passes is different for different observers. And we have cold, hard proof. Take these little things called muons. They're unstable particles that get created way up in our atmosphere, and they have a really short lifespan. They're zipping towards us at nearly the speed of light. Now, classical physics predicts that if you start with, say, 1,000 of them at the top of a mountain, only about 45 should survive long enough to reach sea level. But when we actually go out and measure it, we find around 540 of them make it down. So, why? Because from our perspective here on Earth, the muons' internal clocks are ticking incredibly slowly due to time dilation. Their short little lifespan gets stretched out, which allows way more of them to finish the journey. This isn't just a theory, it's a direct, measurable fact.
And this is just brilliant because it shows you the other side of the coin. From the muon's point of view, its clock is ticking perfectly normally. So what gives? Well, from its perspective, the distance from the top of the mountain to sea level, the space it has to travel through, has actually shrunk. This is length contraction. An object in motion is measured to be shorter in its direction of travel than when it's just sitting there. So from our frame, the muon's time slows down. From the muon's frame, the distance it has to travel shrinks. And both points of view give you the exact same correct answer. It shows you that space and time are just inextricably linked.
Okay, so this all leads us to maybe the most famous and honestly the most misunderstood thought experiment in all of physics, the twin paradox. It's basically a puzzle designed to really test our intuitions about how all this relativity stuff works.
So here's the setup. You've got two twins, Mary and Frank. Mary hops in a super-fast spaceship, travels to a distant star at 80% of the speed of light, turns around, and comes back. Frank, her brother, just stays home on Earth. Now here's the paradox, right? From Mary's perspective in her spaceship, she was the one sitting still while Frank and the Earth zoomed away from her and then zoomed back. So according to her, shouldn't he be the younger one? It seems like it should be perfectly symmetrical. And that is the perfect question. It gets right to the heart of why this is so confusing. It seems symmetrical, but it isn't.
When we actually run the numbers, there is one definite, unambiguous answer. If the trip takes 20 years according to Frank's clocks on Earth, he will have aged 20 years. But because of time dilation from her incredible speed, Mary's clock will have only ticked forward by 12 years. She comes back home a full 8 years younger than her twin brother. For real.
So what's the deal? Why isn't it symmetrical? The whole key, the one word that solves the paradox, is acceleration. See, Frank on Earth stays in a single constant state of motion the whole time, what we call an inertial frame. Mary does not. She has to accelerate like crazy to get up to speed. Then she has to decelerate, turn her ship around, accelerate again to come home, and then finally decelerate to land. That act of turning around, of changing her inertial frame, is an absolute physical experience. She'd feel the G-forces slam her into her seat. Frank wouldn't. That acceleration is what breaks the symmetry and makes her the one who is unambiguously younger. So if space can shrink and time can slow down, if they're both relative, what's left that's actually real? What's absolute? Well, Einstein's final brilliant insight was to realize that space and time aren't actually separate things at all. They're just two different aspects of a single underlying reality. He fused the three dimensions of space, length, width, and height, with the one dimension of time into this four-dimensional fabric called space-time. And in this new picture, the speed of light creates this ultimate structure, something called the light cone. For any event that happens, like a firecracker going off,
The light cone defines its absolute past, that is, everything that could have possibly affected it, and its absolute future, everything it could possibly affect. Anything outside of that cone is just causally disconnected. It can't affect you, and you can't affect it. And this brings us to the new absolute. While you and I might disagree on the distance and space between two events, and we might disagree on the time between them, we will all agree on the space-time interval between them. It's sort of a four-dimensional distance that combines space and time in a special way. And this interval is invariant. It's the same for everybody. And depending on what it is, we can know for sure if one event could have caused another, if they're too far apart in space to ever affect each other, or if they're connected only by a beam of light. So, in the end, Einstein's theory of special relativity completely tears down our old, comfortable absolutes of space and time, but it gives us new, much more profound ones in their place. The speed of light is absolute. The space-time interval is absolute. And most importantly, the laws of physics themselves are absolute. The whole point of relativity, ironically, is that the fundamental rules of the universe don't change, no matter who you are or how you're moving. And that, I think, is a far more powerful and beautiful idea than the simple clockwork universe it replaced.